Welcome to our final project for CSCI 5551, Spring 2025 at the University of Minnesota. We present Raven TeleOp, a middleware framework that enables intuitive, real-time teleoperation of robots using 6 do-F hand gestures. Our system converts these gestures into motion commands, supporting seamless control across a wide range of platforms, including simulators like KinEval, PyBullet, Genesis, and Gazebo-ROS, as well as real robots, all without any specialized hardware. This framework is low-cost, simulator-agnostic, and robot-agnostic, meaning it works across diverse robotic systems without needing additional equipment. Our objective was to show how gesture-based control can generalize across both simulated and physical environments in a flexible and accessible way. The key to Raven TeleOp's success lies in its ability to leverage RGBD input from the Intel RealSense L515, MediaPipe's robust 21-point hand landmark detection, and our custom pose estimation algorithm. Together, these components enable accurate 6 do-F gesture recognition. The resulting pose commands are transmitted via a ZMQ server to robot motion controllers, allowing seamless, real-time teleoperation across simulators and physical robots, all without specialized hardware. Now, let's take a look at Raven TeleOp in action. Here, Raven TeleOp controls a real TurtleBot 3 robot. The user's hand gestures are translated into velocity commands, allowing smooth motion along a curved, wave-like trajectory. This demonstrates the system's responsiveness, natural control interface, and real-time feedback capabilities. What's even more compelling is the system's resilience. Raven TeleOp performs reliably under suboptimal lighting and can interpret closed fist gestures just as effectively as open hand poses. This suggests strong applicability in real-world environments and indicates that the system remains accessible even for users with limited hand mobility or physical impairments. To evaluate the effectiveness of Raven TeleOp, we conducted a controlled navigation task using a real TurtleBot 3. The robot was required to move from point A to point B along a predefined curved path, with multiple obstacles introduced to simulate a challenging real-world environment. A collision was defined as any instance where the robot touched the boundary or an obstacle. We compared 3 input methods: traditional keyboard control, joystick input, and our gesture-based Raven TeleOp system. As shown in the table, keyboard teleoperation had the slowest average task completion time at 12.5 seconds and resulted in 4 collisions. Joystick control performed better, completing the task in 9.8 seconds with 2 collisions. However, Raven TeleOp outperformed both, achieving the fastest average completion time of 8.2 seconds while maintaining the same low number of collisions as the joystick, just 2 on average over 10 trials. This demonstrates that our system is not only intuitive but also competitive with, and in some cases superior to, conventional input methods, even in physically constrained environments. While the system performs well, we identified a few failure modes. Slippage failures during sharp turns due to traction loss, motion controller failures in confined zones, and model errors, where misidentified hand landmarks introduce spikes in yaw, pitch, and roll, briefly destabilizing robot control. These findings point to areas for future improvement, such as signal filtering and temporal smoothing. In conclusion, Raven TeleOp successfully enables camera-only, gesture-based teleoperation across both simulators and real-world robots, with no additional hardware required. It handles various gestures, adapts to low DOF systems effectively, and while challenges exist for high DOF scenarios like UAVs due to minor pose noise, the system is a strong step toward more natural, inclusive robot control.